Good evening, everyone, from the sunny Southern California. My name is Jen Lange. I'm a product manager from Esri based in Redlands, California. What I'm going to present today is a project I did together with two other team members. My colleague Dr. Witold Frejcek from Esri and Dr. Carsten Lange, an economics professor from Cal Poly Pomona. Our project is to use GIS and machine learning techniques to predict urban growth in a study area in North Carolina. There are three goals that I'm trying to achieve with this talk. First, by explaining the project in a step-by-step manner, I would like to showcase a complete workflow to apply GIS and machine learning together. Since each of our team members have a different expertise and may prefer different technology, I would also like to showcase our experience with collaborations and our experience in combining different technologies. So first of all, what is the goal of this project? Our goal is to develop a machine learning model to predict urban growth. With this model, we would like to answer two questions. Number one, which locations in our study area would be most suitable for urbanization? Number two, how probable or what's the likelihood is urban development in a specific location in the study area? For the study area, we chose to focus on the Research Triangle area in North Carolina. The area covers 3 cities, including Raleigh, Durham, Cary, with 3 research universities. The size of the study area is roughly 80 miles by 50 miles. This study area was chosen for its relatively limited size and because the land use patterns in this area are geographically typical for the United States. Our project team consists of 3 members. My colleague Witold and I work for Esri. We're trained GIS professionals with many years of experience in geospatial technology. Naturally, our technology preference would be ArcGIS products, such as ArcGIS Pro. Another team member, Dr. Carsten Lange, is an economist and a data scientist. He has the expertise in data analysis and machine learning algorithms. Dr. Lange prefers working with R, a programming language for statistical analysis. Our different preference in technologies created some challenges in the collaboration experience. The biggest challenge was that we must constantly move large amount of data between ArcGIS Pro and RStudio. Not only is it a time-consuming process, it also poses risk of compromising data integrity and hindering efficient collaboration. For example, whenever a change was made in the GIS dataset, we had to create several intermediate datasets, store the datasets, and exchange them. Our solution to this challenge was to use the R-ArcGIS Bridge. R-ArcGIS Bridge is an Esri open source R package. What this bridge does is to allow dynamically passing of data between ArcGIS Pro and R. Leveraging R-ArcGIS Bridge, our team was able to automate the analytic processes and maintain changes made to the underlying GIS datasets. Another major benefit of the R bridge is that we can now easily combine the spatial data processing and mapping capabilities of ArcGIS Pro with the statistical modeling capabilities of R. The source of the data used in this project is from National Land Cover Database. These are raster datasets with 30 meters resolution. The database is updated every 5 years based on satellite images covering the complete United States. The original NLCD datasets are classified with 16 land cover categories, as which you can see here on the screenshot. As for the predictive model, we chose to use random forest, a supervised machine learning algorithm based on multiple decision trees. The prediction output includes the prediction results, whether or not a raster cell becomes urban, and the probability, which is the likelihood of the prediction. Here's an overview of our project workflow. First, we prepared and processed the land cover raster datasets and the additional explanatory datasets in ArcGIS Pro, and then we passed the data via R-ArcGIS Bridge to RStudio as an R data frame. The data was then modeled and trained in R using the random forest prediction model. And finally, the prediction results were passed back to ArcGIS Pro via our ArcGIS Bridge, and we used ArcGIS Pro to visualize the final results. Now I'm going to share more details in each of these steps. The first step is to prepare and process the spatial data sets in ArcGIS Pro. So we downloaded the NLCD land cover raster data for our study area for 2001 and 2016. As you may recall, the original raster data provides 16 land cover classes. In ArcGIS Pro, we reclassified the data into two categories. The two categories are urban and non-urban land use types. For example, the original classes such as developed open space, developed low density, medium density, and high density were all classified as urban, and the rest of the categories were classified as non-urban. We then compared the land cover for 2001 to land cover for 2016 in order to identify areas of urban growth during this period. So from this comparison, a new raster dataset called Change to Urban was generated as the output. Cells categorized as non-urban in both 2001 and 2016 were categorized as became to urban equals to no. Cells that are categorized as non-urban in 2001 that changed to urban in 2016 were categorized as became to urban equals to yes. Cells categorized as already being urban in 2001 were not considered in our research because the project's focus was on urban growth. The subset used for the study area consists of 10.6 million cells. In the study area, 1.7 million cells that were already urbanized in 2001 were not considered. The remaining 8.9 million cells either stayed non-urban or changed to urban between 2001 and 2016. This data was used for the model. Next, we have to collect and prepare data that potentially can explain urbanization. These will be used as explanatory variables for the predictive model. Again, we used ArcGIS Pro to create these datasets. 7 new raster layers were created in ArcGIS Pro, including drive time to the nearest urban centers, proximity to freeways, proximity to flood zones, proximity to environmentally protected areas, and slopes. Now we have 7 explanatory spatial datasets plus the layer with become urban equals to yes or no. In order for us to use it in R, we need to aggregate all layers into one table. We used Model Builder in ArcGIS Pro to automate the process and document the steps. The result from the model is a point feature class with 8.9 million records. The attributes of the feature layer included the variable to predict, which is change to urban equals to yes or no, and the 7 explanatory variables. Now we have a single feature layer with all the required attributes ready in ArcGIS Pro. Our next step is to pass the dataset to R for analysis. That's when our ArcGIS Bridge came into play. We set up the R ArcGIS Bridge on a computer which had R, ArcStudio, and ArcGIS Pro installed. Then we started RStudio and loaded the ArcGIS binding package in RStudio. This binds the RStudio session to the ArcGIS Pro installation. To pass the feature class attributes to an R data frame, the function arc.open was run with the name of the feature class and its full path to connect the feature class to an R variable. Then arc.select was used to pass the feature class attributes to the R data frame. Now we're ready to train and model the data. This step is done using R in RStudio. As I mentioned earlier, we decided to use random forest to predict urban development. First, the dataset was split into training and test data. The training data consists of 85% of randomly chosen records. The rest 15% of the data were used as testing data to validate the model's performance. Before we could run random forest, we identified a problem with our data. Our dataset was extremely unbalanced. Out of the 8.9 million records, we have about 99% remain unchanged between 2001 and 2016, which means there's no urban development, only 0.01% showing change. This is not all that surprising because a lot of the areas are forest, lakes, and fortunately had not been developed. However, this imbalance in our dataset could pose a threat of the machine learning model, because machine learning models tend to choose the easiest solutions. If we use this imbalanced data, the model would predict no change to urban for all cells due to oversampling. In order to balance the dataset, we ran a technique called SMOTE from the DMWR package in R. As you can see from the table to the left, in the original training dataset, the majority class had more than 7 million records, while the minority class had only 9,000 records. After SMOTE was applied, the majority class was reduced to 3.6 million records, while the minority class was increased threefold to 2.7 million records. The balanced training dataset was then used to train the random forest model. Then we applied the trained model on the test dataset to predict if each record changed from non-urban to urban. Since the true values were already contained in the test dataset, we could validate the predicted values to gauge the accuracy of the model. From the approximately 1.3 million records in the test datasets that did not change to urban, 1.2 million records were predicted correctly, which account for about 95%. From the 1,500 records in the test dataset that did change to urban, 1,400 records were predicted correctly. That's about 89%. So we can conclude that the random forest prediction model showed 89% accuracy of urban development and 95% accuracy of non-urban development. Once the predictions were modeled, the resulting data frame needed to be transferred back to ArcGIS Pro for visualizations. Again, we used our ArcGIS Bridge in this step. In RStudio, arc.write was used to write the data frame from R to the original geodatabase in ArcGIS. The resulting table in ArcGIS Pro included attributes containing the prediction results from the random forest model. Also, the predicted probability for each record changing from non-urban to urban also included. Next, we use the Add Join tool in ArcGIS Pro to join the original point feature class with the table passed from R. Then we created a raster layer using the Point to Raster tool. We used ArcGIS Pro to visualize the final prediction results, which is ideal because of the advanced mapping capabilities of ArcGIS Pro. The predicted patterns were as expected, with projected urbanization areas being closely located to existing developed areas and roads. As I mentioned earlier, our prediction results was based on 2016 land cover data. What is really interesting is that when we overlaid the prediction results with the 2020 satellite imagery base map, the predicted urban areas matched the actual urban areas showing in the latest satellite imagery, which validated our prediction. To sum it up, this project with ArcGIS Pro and R achieved its overall goal. which is to predict urban growth in this study area. Our team integrated knowledge and skills from GIS and data science to make this project successful. Our ArcGIS Bridge was a key component in creating a smooth workflow. It allowed R to dynamically access ArcGIS Pro data and save our results back to an ArcGIS geodatabase. Before I leave, here are some additional resources for the project presented here. We published an article in ArcUser Winter 2021 issue, and I'm sharing the link of the article for those of you who would like to learn more details. My colleague and I wrote a blog article that provides a summary of the project. The link is also shared here. Lastly, for those of you who are interested in learning more about our ArcGIS Bridge, here's the link to the product page. On behalf of our whole project team, thank you all for listening.